Yeah. So I did want to mention that I have been trying to correct the typos in my notes, especially with the help of Kenji. So I do try to post updated versions with all the corrections up to the point that we've reached. Sometimes the server is a bit slow, so for example, I was not able to upload the most current version right now just because I couldn't connect to Utah quickly enough, but I'll do it very soon. So today I want to get back to talking about flips and hopefully start the proof of the theorem on the existence of flips. So let's remind ourselves what a flip is. So we're thinking of a Kawamata log terminal pair and a flipping contraction. So what's a flipping contraction? So it's a contraction morphism, F, say from X to Z. So it's surjective with connected fibers. So F lowest star of O of X is O of Z of normal varieties, such that the relative Picard number is 1. Well, maybe I'll add, we typically assume that X is Q factorial. And then the most important hypothesis of all is that minus kx plus b is ample over z. And typically you assume maybe that z is affine, so you can just say that minus kx plus b is ample if you prefer. So that's what a flipping contraction is. And remember that the flip, if it exists, is another contraction morphism with similar properties except for one. So the relative Picard number is still is 1, but now kx plus b plus is ample over z. And of course, I forgot to say it. I should say that this morphism is small. So that means that they are isomorphisms in codimension 1. The map contracts no divisors. Does not contract any divisor. Okay, so if the flip exists, I've already told you that then it's given by taking proj of the pluricanonical ring of kx plus b over z. Now maybe I should explain why this is the case, right? So here's the reason. If both of these morphisms are small, then x is isomorphic to, assuming that x plus exists, then they're isomorphic in codimension 1. But then you see that forces the rings of sections of multiples of kx plus b to be isomorphic to the corresponding ring on the flip. Why is that? Well, if I have a divisor in here, I can just push it forward to here. And you can check that a rational function plus this divisor is effective if and only if the corresponding rational function plus this divisor is effective just because of the isomorphism in codimension 1. So those two are the same. But on the other hand, I have that kx plus b plus is ample over z. So really, I certainly know that x plus is given by proj of kx plus b plus over z, right? It's not, I imagine how people came up with this is they said, well, wouldn't it be nice if you had a flip with these properties? Okay, then how can you sort of identify the flip? Well, you have a relatively ample line bundle, so it has to be proj of that. Well, they're isomorphic in codimension 1, so all we need to do is to prove that this ring is finitely generated. So the upshot is that flips exists if and only if I can show that the ring kx plus b over z is finitely generated. Okay, so now we're hoping to prove that they exist in all dimensions, so we need some kind of induction on the dimension. And as usual, the induction on the dimension will be given by doing some kind of adjunction, restricting to a divisor. But there is no distinguished divisor in the picture. So Shokroff came up with an idea known as reduction to PL flips that provides this. So I've not told you what a PLT pair is. So let me first tell you what a PLT pair is. So a PLT pair is a log canonical pair, let's say x s plus b, such that the round down of s plus b is just equal to s. So in other words, I'm saying that when you look at this divisor, the only thing with coefficient 1 is this irreducible divisor s. Let's assume that s is an irreducible divisor. You could assume that it's reducible, but the components are disjoint. But we can just assume that it's irreducible for our purposes. And S is the only non-KLT place. So in other words, what does this mean? It means that if I pick any divisor E over X and I compute the discrepancy, this is always greater than -1 as long as E is different from S. Right? Clearly, S has coefficient 1, so the discrepancy is -1, but it's the only one. So in other words, the pair is sort of failing to be KLT, but it's only failing for one exceptional divisor, for one divisor, this divisor S. Okay, so it's as close to KLT as it can be without being KLT, pretty much. Then it's very natural. So then we have the following claim that S is normal. So I haven't proven Kawamata's result, but the reason is Kawamata's result, as it is minimal. In fact, it's the only one non-KLT center of a log canonical pair. Okay, so I didn't prove that result of Kawamata, but nevertheless, I'm using it. And I can also consider a junction. So I can do Ks plus B sub S is going to be defined by taking a junction Kx plus S plus B and restricting to S. Okay, now be careful. It is not true that Bs is this, just the Bs may be not the same thing as B minus S restricted to S. We've already seen examples of this. If you remember, when we had a cone over a rational curve of degree n, right? So this is a rational curve of degree.
You don't have to stop
Oh, yeah. I don't need to because I built it in. Thank you. So in this case here, I can consider the pair X is a cone, S, so S is a line through the vertex, And we did the computation that kx plus s restricted to s is actually ks plus 1 minus 1 over n times the point P, where P is a point corresponding to the vertex. Right? So in this case, B restricted to S is just 0, but there is a difference. Or more precisely, a different. Okay, so now, so here's another claim. This one is easy to see, is that the pair SBS is KLT. Now, since it's easy to see, why not prove it? So let me attempt to prove it. Proof. So I pick a log resolution, f, from, let's say, x prime to x, a log resolution. And then the natural thing to do is to write that the pullback of kx plus s plus b, you can pick your notation. I like the following, is kx prime plus s prime, where s prime denotes the strict transform of s, plus b prime. Now, b prime may have some negative coefficients, but by definition of this pair being PLT, the coefficients of b prime are strictly less than 1. So now, when you do adjunction, how does it work? It works as follows. You take k x prime plus s prime plus b prime, and you restrict this gadget to s prime, and you get k x prime plus, sorry, k s prime plus b prime restricted to s prime. There's no fancy stuff here because this is a log smooth pair. And now the coefficients of b prime are less than 1, and these intersect transversely, so these coefficients are less than 1. And now what do I have? I have that b sub s is just a push forward of b prime restricted to s prime, right? So in other words, the pullback of k s plus bs is k s prime plus b prime restricted to s prime, where these coefficients are strictly less than 1. This is precisely telling you that SBS is KLT. Okay? The converse is also true. Conversely, if SBS is KLT, then the pair X, S plus B is PLT on a neighborhood near S. Not everywhere, because you could add some divisor with coefficient 1, say, which is disjoint from S. There's no way you're going to pick that up by just checking if SBS is KLT. Any questions? Okay. The converse, which we don't need, is harder. It relies on Kolar-Shokharev's connectedness result. Maybe I can just draw a picture. So if this is X and this is the divisor S, you blew up here to get X prime and some divisor S prime, and now you have a bunch of exceptional divisors. Knowing that SBS is KLT tells you that these coefficients are less than 1. Tells you that the coefficient of this guy is less than 1. But how are you going to know that the coefficient of every exceptional divisor is less than 1? Is this one still less than 1? right? Because the strict transform of S only sees those exceptional divisors for x prime over x, which actually intersect S prime. Now, the point is that by the connectedness theorem, if I look at fibers of this map and intersect them with the non-KLT locus, the stuff with coefficient greater or equal to 1, then that is connected. So if this has coefficient greater or equal to 1, and clearly S prime has coefficient 1, then it has to be connected to S prime by divisors with coefficient 1. So by the connectedness result, if there is any divisor with coefficient greater or equal to 1, there is in fact a divisor with coefficient greater or equal to 1 that intersects S prime. So that's how you go backwards. But we don't actually need that. Okay. Okay, so this was a little digression. I need to make sure that we know what a PLT pair is. So we established what a PLT pair is. And now let me tell you what a PL flip is. So if x, S plus B is a PLT pair, F from X to Z is a contraction morphism, of relative Picard number 1. I won't write it, but I'm still assuming that X is Q factorial. And is a contraction, F is small, minus Kx plus S plus B is F ample, and minus S is F ample. Then we say that F is a PL flip. So the definition is due to Shorokov, as quite a few things in the subject. So how does this differ from a usual flip? Well, first of all, typically I like to think about KLT pairs. This is not quite KLT, right? Because the S has coefficient 1, right? But if you perturb this a bit, consider 1 minus epsilon S, then it will be a KLT flipping contraction. So from that point, it's not so different from a usual flip. The real thing here is that there is a distinguished divisor of coefficient 1, which is relatively anti-ample. So the relatively anti-ample condition tells you that all the interesting geometry is happening inside of S. So if C is a flipping curve, then S dot C is negative because minus S is relatively ample. So that tells you that C is contained in S. Right. So this special divisor sees all the information regarding the flip. Okay, and of course, if you do a junction, you get that minus Ks plus Bs is F ample. Now that doesn't mean that we have a flipping contraction in dimension 1 less, right? Because the picture that you have in mind is probably something like this. You have a freefold. On the freefold, you have a distinguished surface S. You're mapping down to Z. You have some flipping curves, which are getting mapped down to a point. And here's the image of the surface S sub Z. But you see, in this picture, on S itself, we have a divisorial contraction. So it could be that you have a divisorial contraction. It could also be that when you perform the flip, on the other side, you may be extracting more curves than you contracted, or extracting new curves. So the map from S to S plus does not necessarily even have to be a birational contraction. It may extract some divisors. And typically, it could extract divisors that sort of live on the terminalization of S, if you know what that is. Okay, so I'm trying to make the point that, yes, S sees the flip, but it's not a flip for S. It's a more complicated situation for S, somehow. Okay? So I can't just say, oh, well, S has dimension 1 less. I'm just going to flip it on S and end the story there, right? In fact, somehow, I have to do something a bit more general than a flip on S, but then I also have to show that I can sort of glue that back into the ambient variety. Okay, so now I'm going to try and explain how the procedure actually works.
I have a question.
Yes, please.
So minus S was F4.
Mm-hmm.
So when you go to the other side, S is F plus sample, right?
Yeah, so in fact, I know what you're about to say. It could happen, in fact, that the curve comes out of S plus.
Yeah, so
Yeah, yeah.
do you expect that it could like extract some divisors? S plus contains more divisors.
Well, when you do the proof, at some point of the proof, you have to pass. Okay, I'll just say that some of the buzzwords, and maybe it will ring a bell to you or not, but I'm going to get into some details. So you have to show that the restricted algebra is finally generated. And if you read Corty's paper, what he does for free folds is the first step is to go to a terminalization and figure out what the restricted algebra is on the terminalization. That procedure.
No, my question is more naive. So S plus could contain more divisors.
Yes, yes. All I'm saying at this point is that I have no good reason to tell you that it doesn't contain more divisor. And in fact, I believe that there are examples where it does contain more divisors. Yeah. And certainly there are examples where it's a divisorial contraction on here. Okay. Okay, so before I tell you about Shawker's theorem, well, so first there's a theorem due to Shawker, which we will not do the proof of. It's not hard, but it's quite technical. You have to mess around with pairs quite a bit. Flips exist, the usual flips, according to the first definition, if and only if PL flips exist. So going this way is trivial. Going this way requires some work. Yes. Okay. So one direction is trivial because if you have a PL flip, then it is also a KOT flip by the argument I told you. You replace S by 1 minus epsilon S. The map will still be a flipping contraction. It will still be negative with respect to that divisor. Right? So where is the condition? Minus kx plus b is F ample certainly implies that minus kx plus 1 minus epsilon S plus b is F ample. Being F ample is an open condition for epsilon sufficiently small. And so I can, instead of flipping with respect to this divisor, I flip with respect to that divisor, but it's the same operation. So that's why I'm saying one direction is obvious, but the other direction requires some work. You have to show somehow that...
Sorry, so I was wrong. So if PL flips, KLT flips is easy. That's what you said.
No, what I said is if flips exist for KOT pairs, okay, maybe let's emphasize KOT flips. If KOT flips exist, then PL flips exist. Because a PL flip is essentially almost KOT, right? It's PLT, almost KOT plus extra stuff, this minus s business. The other way around is harder. You have to, so what the idea is, you have this nice flipping contraction from x to z. You pass to some log resolution, some interesting log resolution. So, and then you find some auxiliary pair, kx prime plus b prime. This will be a DLT pair. And you run your minimum model program with respect to this pair here. And you show that the output of this minimum model program, let's call this xm. So at some point you arrived with kxm plus bm is going to be nef. So when you're running something for a DLT pair, you have lots of divisors with coefficient 1. So it's reasonable to expect that each time you get to a divisorial contraction or a flipping contraction, there may be a distinguished divisor S, and you can cook up a PL flip with respect to that. I'm not saying that any of this is obvious. It requires quite a bit of work. So this procedure just uses PL flips. And then you have to do something else of a similar nature, which I'm not going to discuss. And then the corresponding log canonical model. So this is just taking something like proj of R of kxm plus bm gives you the flip. So the only thing you should take from this diagram is that in order to prove Shocker's theorem, you start by taking a log resolution, constructing an interesting auxiliary pair, running some minimum model programs with respect to this pair, which always only involve PL flips, and then at the end, at the output, maybe you apply the base point free theorem, and that's going to, and then you have to show that what you end up with is really your flip. None of this is supposed to be obvious. The proof is, if I remember correctly, about 2 or 3 pages, but quite dense pages with, lots of auxiliary objects in them. So, yes.
At the end, when it becomes that, it could have coefficient 1, no?
Okay, well, yes, there are little, so maybe the stuff with coefficient 1 are just exceptional divisors for this map.
Oh.
Or maybe, a little closer to the truth, you do increase some of these coefficients to 1, but then there's another step that I haven't really written down, which is to scale back down those coefficients that got a bit too big.
At the end, you can use the base point free theorem. Okay.
Yes. And so yeah, this is.
Sorry.
No problem. This is. I'm trying to convey that it's not a triviality. So I guess it's okay if we don't understand what the steps are. It's not hard, but it is very technical. Okay. So what is sort of a key point, but also a bit easier to convey what the idea is behind it, is how to show that PL flips exist. So now we're going to focus on PL flips, and remember that in order to show that a PL flip that a flip exists in general, we need to show that a certain algebra is finally generated. So what algebra? We really want to show that the algebra whose graded pieces consist of kx plus s plus b, sections of multiple of this. We want to show that those are finally generated. Okay, now we have this distinguished divisor s, so we can look at the map onto m ks plus bs, given by a junction. And the most interesting thing, these maps in general are not surjective. It's easy to write examples where it's not surjective. So you look at the image of these maps, and you can take the direct sum for every m greater or equal to 0. And this is a fancy object, so you give it a fancy name. So we call this R sub S kx plus S plus B. It's the restricted algebra. And here's another theorem of Shawcroft, which is also not very deep, but this one I do want to explain in detail. Theorem of Shawcroft says that PL flips exist if and only if the restricted algebra, is finitely generated. Okay, so one direction as usual will be trivial. So this direction should be trivial. You see, if the flip exists, then I know, you know that the direct sum of H0 of M kx plus S plus B, so this is the full pluricanonical ring. So I should be saying over Z, but I'm assuming that Z is affine, so I'm sort of suppressing that. So this is finitely generated. But by definition of the restricted algebra, we have a surjection onto the restricted algebra. So we're done, right? Because if this is finitely generated, then whenever you have a surjection, that's finitely generated. Just take the generators of this guy and push them forward. Okay, so that direction is easy. The other direction is hard, right? Because the other direction, you have that, well, you have, let's call this map phi, well, this will be the nth graded piece. So you have the kernel of phi goes to R kx plus S plus B goes to Rs kx plus S plus B. So suppose I know that this is finitely generated. How can I conclude that this is finitely generated? Well, it will be enough to show that the kernel is finitely generated, right? Because you lift generators of the image, and then you take the generators of the kernel, and you'll get the whole thing. So why is this finitely generated? So roughly speaking, I'll make it precise in a second, you should think that this is a principal ideal, and in particular, it's finitely generated. Yes? Well, no, yeah, a principal ideal in here.
Then,
it's clearly an ideal, but principle is not clear.
okay, but why does that imply the middle will be finitely generated?
Oh, okay, so I'm looking for generators of this guy.
Yeah.
So roughly speaking, I take generators of this guy, lift it here, plus the generators of the kernel. Okay, so okay, so this is a big question mark. So we need to understand why the kernel of this map is finitely generated. So let me remind you, and we already discussed it, but I'll use it freely. Recall that we have these graded rings. R is a direct sum of Rm, is finitely generated if and only if the corresponding cave truncation is finitely generated. Right? We discussed this before. You view this as a ring of invariance in here. So if this is finitely generated, then that's finitely generated. And if this is finitely generated, well, everything in here is integral over that. And so by theorem of Noether, that's also finitely generated. Okay, so I'm attempting to show you that under the hypothesis of a PL flip, this is where we're going to use that minus S is relatively ample. Then under those hypotheses, the kernel is finitely generated.
Are you actually claiming that the kernel is a principal ideal?
Well, up to some truncation, yeah.
You're only going to prove finitely generated.
Yeah, I'm only going to prove finitely generated. But, you know, after some reductions, it will become a principal ideal. Okay, so let's start by pick S, which is linear equivalent to S prime, but they're different. Okay, so if you're not used to this business, this will probably bother you immediately because minus S is F ample, so S is negative. How can it move? Well, don't forget that we're looking at a birational morphism, so you're really thinking that X is mapping down to Z, where we're thinking that this is affine because every question is local over the base, right? So you have a lot more degrees of freedom. In particular, for example, there is an effective exceptional divisor, so you could have anti-effective divisors which are relatively ample. Okay, so what I really should have said is in this situation, the base locus of any linear series is going to be contained in the exceptional locus of this map. Right? So since the exceptional locus is just codimension greater or equal to 2, clearly S itself cannot be contained in the stable base locus or in the base locus. So I can pick another. I can move it around.
Are you assuming S prime is irreducible also?
Yes. Oh, am I assuming that S prime is irreducible?
There.
I probably don't need to, but I think I can if I want to, because if I pick a general one,
Yes.
in fact, the general one will even be normal, right? Because if you have a family and one fiber is normal, then nearby family are normal. Again, I don't need it, but I think you can assume that S prime is kind of nice-ish, since S is nice. Okay, so in other words, we have that S minus S prime is the linear equivalent, so the difference corresponds to the zeros and the poles of a rational function. Let's say G. Now, I'm going to use that the relative Picard number is 1, so I know that A, kx plus S plus B is numerically equivalent over Z, but Z is affine, so you can kind of ignore the over Z, to BS prime. Or BS, it doesn't matter, right? Because S and S prime are certainly numerically equivalent. So what am I saying here? Well, you see, the relative Picard number is 1. Both of those divisors are relatively anti-ample over the base. So that one has to be a positive multiple of the other, positive rational number multiple. And so let's clear the denominators. So A and B are positive integers. Okay, hopefully I don't lose my notes because now I would like to promote this to actually having linear equivalence. So may assume. Now, why is that? Okay, let's think about it for a second. So first of all, okay, well, let's prove it. First of all, maybe I should have written it as A kx plus S plus B minus BS prime is numerically equivalent to 0. In particular, this is relatively nef and relatively big. When you have the zero divisor is clearly nef by any measure, and the map is birational, so any divisor is big, even 0, right? So this is anti-intuitive. So then the base point free theorem says that some multiple of this, let's say m times the whole thing, a kx plus s plus b minus b s prime, is generated, globally generated. But if you have a divisor which is numerically equivalent to 0 and globally generated, there's only one conclusion: it has to be linearly equivalent to 0. Okay, so now I replace a by m times a and b by n times b, and I get linear, honest linear equivalence between these two guys. Okay? Replace a to ma, b to mb. Okay. So really here I'm using that I has sort of a final contraction to apply the base point free theorem. So now, okay, so r kx plus s plus b is finally generated if and only if r of s prime is finitely generated. Okay, what did I do here? Well, this one is finitely generated if and only if, okay, I can do the steps in between. So that's finitely generated if and only if the ring corresponding to a kx plus s plus b is finitely generated. But that's equivalent to the ring generated by b s prime being finitely generated, and that's equivalent to this statement. Just because the ring is finitely generated if and only if the corresponding truncation is finitely generated. Okay, so I'm inching towards, so finally, the kernel of the map from R of S prime to R S of S prime, okay, I should have said, and Rs kx plus b plus s finally generated implies or is equivalent to Rs s prime is finally generated by the same argument. Okay, so now I look at the restriction map. So all I've done so far is argued that instead of looking at this exact sequence, the one with kx plus s plus b and its restricted algebra, I can look at the exact sequence corresponding to s prime. Okay, so I want to look at the kernel of this. So let's think about this for a second. So suppose I have, let's look at the nth graded pieces. So what does the section in here correspond to? It corresponds to a rational function such that, let's say fm, such that when I add ms prime, yes, this is correct, this is effective, right? Now, if this is mapping to 0, right, if it restricts on s to 0, that means that, in fact, this this divisor, so fm plus m s prime, vanishes along s, so it's the form s plus d, where d is effective. Okay, but then that means that fm over g is plus m minus 1 s prime. Hopefully I get my signs right here, is equal to d, which is effective. Okay, let's see what I did. The poles and the zeros of g are s minus s prime. So if I divide by g, it's s prime minus s. So if I divide by g, I'm getting rid of a copy of s prime on one side and a copy of s on the other. Right? Or in other words, if I multiply this by g, then I have to, on this side, I have to add s minus s prime, and the minus s prime becomes that one. So I did the computation right. At least it seems to me I did it right. Okay, so what is this saying? This is saying that this element of the kernel, so this means that Fm over G corresponds to an element of H0 of m minus 1 S prime, right? So it's saying that the elements of the kernel of this map are multiples of H0 m minus 1 S prime times G. So it's a principal ideal generated by G. So that's right. So this is the graded piece in degree minus 1 multiplied by this function G. So hopefully, well, anyhow. So what I've done is after this reduction, I've shown that the kernel is a principal ideal, so it's finally generated. Of course, I mean, it doesn't really mean the original thing is a principal ideal because you sort of had to clear denominators and go through these truncations. So, all it tells you essentially it's, in the integral closure of this principal ideal, which is, says nothing. It's just finally generated. Okay, so that's the reduction to PL flips due to Shokharov, and then the statement that all we need to do is show that the restricted algebra is finally generated. Now, I'm sure Shokharov got very excited when he saw this, because he says it would be human to say, if phi from Rkx plus S plus B to Rks plus Bs is surjective, then we are done by induction. Why is that? Well, this is certainly the dimension of S is less than the dimension of X, right? So it's an easier problem in some sense. And it's a KLT pair. So the ring is finally generated. Right, so if you can prove existence of minimal models, then you can show that the rings are finally generated, always, in fact. Right, remember, so if on the minimal model the boundary is big, that's just a base point free theorem. Itachi Kx plus B becomes semi-ample and hence finally generated. But using the reduction of Mori and Fujino, actually we showed that for any KLT pair, the ring is finally generated. So I don't even need to worry about that. Of course, in this setting, it's a birational contraction, so B is even big. Okay, so, and once you can prove existence of flips, then you can get minimal models in the next dimension, and there goes your induction, right? So the sort of idea for the proof by induction is minimal models in dimension x equals n minus 1 implies existence of flips for dimension of x equals n, and then this implies existence of minimal models in dimension x equals n, and then you just repeat. That's sort of the idea behind the induction. Okay, so we just have to prove that it's surjective. Well, unluckily, it's not true that it's surjective in general. Okay, So it could happen that this map is not surjective. And what is the reason? Psychologically, what could be going wrong? Well, here's your x, here's your flipping contraction onto
I'm sorry.
Yes.
So assuming that the full minimal model, then in dimension 1 less.
Yes.
I understand if you assume this surjection, then flips exists.
Right.
But then the next arrow, don't you need this termination?
Right, but you don't need every termination. You just need termination of the minimal model program with scaling. Okay, so now.
Okay, sorry.
Right, but there is a little bit of a point to what you're saying.
No.
The induction has to be done carefully so that all the pieces are in the right place. So this is just a bit of an intuition. You have to do some sort of special termination so that you don't.
But you're saying if this door surjected, then it would be done.
Right. So maybe, the minimum model program for free folds was known a long time ago. And then Shokuro was trying to prove existence of flips in dimension 4, which is very hard. So he looks at this map here, and he says, well, free dimension was established a long time ago. Now I get flips in dimension 4.
But you're saying this is not surjective.
It's not surjective. And he realized that. I'm not saying that he missed that, but I'm just saying the first time you write this down, you get excited. You're like, I'm almost done. Unluckily, it's not surjective. The reason why it's not surjective, typically, you could have your flipping contraction may coincide with the component of this boundary Bs. So maybe this boundary is even empty. But this free-fold is singular along this curve. So it causes this curve to appear in the boundary of the restriction of kx plus s plus b to s.
I'm lost. I'm sorry. You said ds is a divisor in s. Yeah?
So it could happen that a component of Bs is contracted.
Oh.
There's no reason why that can't happen.
Okay.
That happens precisely when on S you have sort of a divisor contraction, or on the ambient variety a flipping contraction. Okay, so this component of Bs is sort of in the stable base locus. So the images of this map automatically have to vanish along that component. Looks like a bit of an artificial situation, right? So at the very minimum, the image of phi has to be contained in the ring corresponding to Ks plus Bs. I have to throw away the components of Bs which are in common with the stable base locus of the restricted linear series Ks plus S plus B. So this is a real mouthful what I've written here. So all I'm saying is if there's a component of Bs that is also contained in the stable base locus of Kx plus S plus B on the ambient variety, then certainly the image of these sections have to vanish along there. So I certainly have to throw those away. Okay, so I guess our biggest contribution was to figure out exactly how to deal with this problem. Right? So roughly speaking, what we did is we figured out once you make this correction, it does become surjective.
It's equal.
Yes, it then becomes equal, and then you can apply this.
So image is equal.
It's not equal to this guy.
No, but
Yes. Yeah. Well, I have to add a few technical conditions, right? If only you have to go to the terminalization on computer. But
this inclusion at the bottom becomes
right. So let me write that down formally, which is what you were saying. So the goal, since that doesn't work, the goal now becomes to show that the restricted algebra, Rs of kx plus b plus s, is equal to the algebra corresponding to ks plus, let's say, a divisor theta, where theta is somewhere in between 0 and b sub s. And then this will be finally generated by induction on dimension.
Is it truly equal or up to some multiple thing?
Well, certainly we only worry about the multiples, but I think it's truly equal. I think it is truly equal. Yeah, it probably is.
So you you identify the restrictive algebra as the law canonical ring of some T pair.
Yeah. Yeah. Once it's sort of true asymptotically, these things tend to be true on the nose by applying Kawamata-Vivek vanishing. Okay, maybe I should walk that back. Maybe it's true on the nose every time this guy is an integral vowel divisor, something like that. Okay, so maybe now is a good time to take a little break, and then the next thing I clearly want to do is start telling you about precise results on how to compute the restricted algebra. So how can I extend sections from a divisor to the ambient variety? This is very similar to Sue's stuff on deformation invariance of plurigenera, where he extends pluricanonical forms from one fiber to nearby fibers. Here we want to do it from S to the ambient variety. So we'll start talking about that in the next hour.
Yes, you're allowed to argue before. Preemptive question. No, but I think some people have come back.
Okay, so what's your preemptive question?
You wrote this B wedge space.
What does B wedge mean?
No. Or yes, including that.
So look, let me talk a little bit about notation. So when you have two divisors, B and B prime, so what does this symbol mean? So B is a sum of bi, B prime is a sum of bi prime, di. Then this is the biggest divisor in common, so this is the sum of the minimum between bi and bi prime of bi. So you just decrease the coefficients to match the minimum of the two divisors.
Okay, would you write down the formula for theta again?
For theta, okay.
Yeah.
So the formula for theta was something like, really you have to do it on a high birational model, but let's say it's something like Bs minus Bs wedge the stable base locus of the linear series Kx plus S plus B sub S. So let me try and explain more details of this. So first of all, what does this symbol mean? Okay, so that symbol there, Kx plus S, well, in general, for a divisor D, D sub S will be contained in the full linear series corresponding to the restricted divisor. So these are those divisors which are in the image of the restriction map. So you can take a divisor in the ambient variety and restrict it to S as long as it doesn't contain S in its support. If it contains S in its support, it just goes to 0. It doesn't give you anything. It's in the kernel of that map. And so this is a sublinear series of this, right? And so, of course, everything in the image of that map has to be in this sublinear series. So it has to vanish along the base order.
So is that a B, this capital D parenthesis?
I can put another parenthesis like this, if you like.
I see.
Yes. That's the stable base locus of that restricted linear series.
I see. But how do you determine the coefficients?
The coefficients? Okay, so when this is shorthand for something. So when you have a linear series, you can determine the coefficients just by taking the minimum along all elements of that linear series of the multiplicity along a certain divisor. So really, maybe you would be happier if I wrote this here.
No, still not. I'm so happy because if your algebra is not finally generated, the stable locus may have some irrational coefficient.
That's a very good point, Kenji. That's why the proof is not going to be so easy. The limits exist as real numbers.
Yeah.
So that is one of the difficulties in the proof that we will see. We'll have to worry once again about the fact that theta, so the proof consists in two steps. One, showing that theta is a rational divisor. You're running ahead, but yeah, that is a real issue here.
Okay.
It's not hard to show that you can take this limit, but it takes work to show that it's a rational number. And there's some Diophantine approximation somewhere in there to get things right.
Okay. That makes me happy, yes.
Okay. It makes you happy to know that things are harder. Yes. Things are indeed harder.
Because if theta is irrational, like even if you realize it as a KLP there, that may not be. That's not good. Then the algebra will not be finally generated. Unless the irrational stuff is contained in the base locus. So you will tell us how to show the rationality?
Hopefully, yes.
Okay.
That's
a part of the.
That's part of the proof. Yeah, that's one of the important parts of the proof.
Sorry, that was preemptive.
You had a point. Okay, I'll jump back to multiplier ideal. So now, in this context, I'm thinking of a pair XB, which is log smooth. So what do I mean by log smooth? I mean that X is smooth, B is simple normal crossings, and has coefficients 1. So let me call that a reduced divisor. Okay, then I want to consider now a Q divisor, which is effective Q divisor. And I want that the support of B does not contain any strata of B. So if this is what B looks like, it can't go through this point. That would be a strata, but D could be something like that. Okay. So I'm trying to define a certain kind of multiplier ideal sheet. So let me consider f from y to x log resolution of x and b plus d. I guess the important part is d there. And then I'm going to write that ky plus gamma is a pullback of kx plus b plus e. And I make the usual convention that gamma and e are effective with no common component, and now that I introduced the notation, I can just write that as gamma wedge e is 0. They have no common component. Okay, so having said that, I'm ready to define the multiplier ideal sheet. So this, in the literature, is often referred as some kind of a joint ideal. So this will be the multiplier ideal sheet of D with respect to the pair XB. So it's just going to be the push forward of all of Y, E, minus the round down of C, pullback of D. Okay, so maybe what you're mostly used to is if B is empty, then this ideal is just the usual multiply ideal sheaf of the divisor CD. Let me not put the C here then. Okay, let me put a C and let me put a C here. I mean, D is a Q divisor, so I can do it whichever way.
What is C? C
is C is some rational number, or even real number if you want. Okay, so C is really not necessary because you can just replace the Q divisor D with the Q divisor CD.
Chris,
yes.
I think your microphone is off.
And now it's on. Thank you. Okay, sorry about that.
Oh, wait. Is it on?
Yeah, it's. I can hear the echo. It's on, right?
Wait, hold on a second. オンになってます？
ちょっと待ってください。何か。
We're good?
OK です。OK です。
Yeah. No, but I can hear the echo. I'm pretty sure it's on now.
Sorry.
No, but my bad.
Wait, hold on.
Okay. So maybe if you don't like the C there, just do the ideal of B with respect to a Q divisor D is a push forward of OY E minus the round down on the pullback of D.
No. So there's a little bit of statement there. So you are saying since the D does not contain any strata of B, so therefore you can take log resolution satisfying gamma E effective and gamma wedge E is equal to 0.
No, there's no statement. You can always do that. It's not. Why not? I mean, you can always, if you have a pair, you can always pull it back, and you can, the difference between the two, you can always split it up. I've not made any interesting claim about gamma and E. Just like the positive part of the difference, I put it on this side, and the negative part on that side. There is no intelligent statement there. And now, once I claim some vanishing, there'll be an intelligent statement.
But I was, that's not so clear to me how you choose gamma and E.
I think this time you're getting worrying about nothing. Write ky minus the pullback of kx plus b equals g. We can certainly do that, right?
Yes.
Well, you have to choose a ky whose push forward is kx, but once that is done, you can do this. Now, write, certainly g can always be written as e minus gamma, where these are both effective with no common components.
Oh, okay.
That's all I'm saying. So yeah, so in this case, you're worrying about tempest in a teacup. Okay, so now it turns out that this ideal does not depend on the log resolution. So this is, it's not hard to show, but it takes a few minutes, dependent of log resolution. Now, for example, we should be able to check the following. So suppose that we have b prime, which is less or equal to b, c, which is greater or equal to c prime, and d, which is greater or equal to d prime. Hopefully I got all the inequalities right. Then it should be clear that the ideal corresponding to b, c, d is contained in the ideal corresponding to b prime, c prime, d prime. Okay, so why would that be? Well, okay, so if b is less or equal to, if b prime is less or equal to b, then that tells you that gamma prime minus e prime is less or equal to gamma minus e. Right? You're just comparing the pullback of kx plus b and the pullback of kx plus b prime. And b prime is less or equal to b, so when you pull them back, you'll get something smaller. Okay, so you stare at this for a second and you convince yourself that this means that E is less or equal to E prime. Okay, so now from these two, you also have that C pullback of D is greater or equal to C prime pullback of D prime. So then you obtain that E minus the round down of C F upper star of D.
I'm sorry.
Yes, please.
But, oh, you're right. You flipped the primes. Yes. I'm sorry. You're right.
This is now I got confused. E, okay.
Sorry,
this is less or equal to E prime minus the round down of C prime pullback of D prime. Right? Because if I have this inequality, then I have a similar inequality with the round downs, and then I put it in there. And so by the way, E and gamma are integral divisors in this picture. So now this tells me that the push forward of OX E minus the round down of C pullback of D something with respect to the push forward of OX, sorry, this should be OY. Luckily my Y's looks like X's, E prime minus C prime F upper star of D prime. Okay, so which way does the inclusion go? Let's see, this is a bigger divisor. So I'm requiring less vanishing, so it should be more sections. So we should have this inclusion, and yes, things match, right? This is this ideal, and this is that ideal. So there's sort of an obvious monotonicity for these ideals. Okay. Now, okay, you may be wondering what the point here is, and the point is going to be apparent in 1 second. So remember, our goal is to learn how to extend sections from a divisor to the ambient variety.
Where did you use this support of D not obtaining square root of D?
I haven't used it yet, but morally speaking, that means that if you consider DB plus a little bit of D, it will be a DOT pair. It will at least be log canonical, because if I were to add an effective divisor containing a strata of B, it's no longer log canonical, right? I cannot expect any good behavior. Proposition. So X is smooth, B is a reduced simple normal crossing divisor, D is an effective Q divisor whose support contains no strata of B, just the same hypothesis. So here's the statement. For any component S of B, there is a short exact sequence. 0 goes to the ideal of B minus S, comma D plus S, goes to the ideal of B, comma D, goes to the ideal of B minus S restricted to S, comma D restricted to S, goes to 0. Okay, so I'm essentially doing some kind of adjunction here. I'm restricting to divisor of coefficient 1, and this is what appears as the kernel. So if you only cared about honest multiply ideals, for example, if you only cared about the case where this is 0 and this is 0, you would still want to relate that ideal with the restriction to S. The way they relate would be through this ideal, where now there would just be the component S here. So to one of these mixed objects. Now, if you have a divisor and you want to do that several times, you will necessarily be led to considering these adjoint ideals. So I'm just saying that if you believe in multiply ideals, which so far maybe you have no reason to believe in, then you sort of, these automatically come bundled in a package with these fancier version of multiply ideal sheaves. So let me try and prove that we have this kind of short exact sequence. So what what I'm going to do is I'm going to fix a log resolution, but not just any log resolution. I like to make my life easy. You don't have to do this, but it's easier. So f from x prime to x, which is an isomorphism at the generic point of every strata of B. Okay? So in other words, I don't want to extract divisors corresponding to log canonical centers of B. Now, this is not completely obvious that you can do such a thing. You know, given any example, you'll be able to do it. In practice, it requires work. This is actually a theorem of Szabo that you can do this kind of resolution. So now I'm going to write kx prime plus b prime. I apologize, I'm changing the notation slightly from there, but I better go with my notes or I'll end up making a mistake. So I'm going to, this is what I've typically, instead of writing y and gamma, I wrote x prime and b, and I'm writing the pullback of kx plus b. There'll be two affected divisors that I split up in that way. Okay, but at least I kept the notation for E consistent. That's what we've been using. And let's denote by S prime the strict transform of S. And then upstairs I have a clear short exact sequence, which I'll write in divisorial form. Okay, so let's look at this short exact sequence. This one is really obvious. Here's a divisor, a Cartier divisor. I add S prime, so I get an inclusion into this corresponding sheaf, and then I restrict to S prime. That's just the standard, you know. O minus S to O restricted to S, twisted by a line bundle. So nothing special there. So if I'm going to obtain from this one, if I'm going to obtain this one, I need to push forward the short exact sequence, show you that R1 F lower star of this is 0, and that the push forward of these terms give me that term, right? So let's look at what the push forward does here. Okay, so what's the formula? Yes?
I'm a little worried. There's this, you commuted the round down with the restriction at the end.
Well, it's a log resolution. That doesn't work in general. So Kenji is worried about the following fact. If you have a divisor, if this is S and this is D, D restricted to S round down is not the same as the round down of D restricted to S. Perfectly good point. However, if the divisor looks like this, then you're fine. The coefficients will be the same when you restrict. On a log resolution, that is true. Okay. So that's the same reason that when we do adjunction, downstairs things you have a different, but upstairs you're just restricting the divisor. Okay, so now I'm doing the push forward. Okay, here I see E minus round down pullback of D. I go look for my formula of the ideal. Oh, wait a second, that is precisely IBD. Okay, so this one is just definition. Okay, so now here, what am I claiming? So this should be somehow, I'm hoping to say that this is IB minus S, D plus S. So in order to claim that, well, I need to be able to reinterpret this as the gadget coming from B minus S, right? And this part here should be minus the pullback of S prime. So, so let's see that. Let's look from this picture here. I want to think of the pullback of kx plus b minus s here. Okay, so now when I pull that back, I will get kx prime plus b prime minus the pullback of s equals this plus e. I did nothing interesting here. I just added and subtracted. I just subtracted on both sides the pullback of s. Okay, so now let's see what's going on. So what I'm hoping here is to get the pullback of d plus s. Okay? So then, right, what I want is the other e, let's call it e tilde, minus that, where e tilde is the one that should be coming from this pullback here. So we just need to stare at it for a second, and it's supposed to pop right out at us. So from over here, the divisor that well, maybe I should, okay, the divisor that I'm getting here, I can write it down. This is going to be E plus f upper star of s minus s prime. Okay, so this divisor is equal to that one. That's what I'm claiming. Yes, because S is Cartier divisor, so it goes in and out of the round down with no problem. And so here I have minus the pullback of S. Here I have plus the pullback of S. They cancel, and then minus S prime and minus S prime. Okay, so that's looking good. So now I have to just make it appear here in the same fashion, and I will be happy. So, so here is minus. So yes, minus the pullback of why am I getting confused? Okay, so I can take this to the other side, and it's still an equality, plus the pullback of S. And now I want to write minus S prime, minus S prime. It worked. Okay, let me try and explain. When I'm doing this, I'm supposed to write here the strict transform of B minus S. B prime minus S prime. What's left is then this divisor, just by computing the differences from here to here. Now here, I wrote down, by definition, I wrote down what's equal to that one. And I observe that what I got is, this is the E coming from B minus S. So B minus S. And inside here, I have pullback of D plus S. Yes. So I didn't do that in the most brilliant way, but since I got so confused and I still managed to get to it, it's probably correct.
You finished it.
Yes. Okay, so now you have to do the same thing over there for the restriction to S. And so that one hopefully is easy, because I can take this one and restrict to S prime. And so I'll get K S prime plus B prime minus S prime restricted to S prime is equal to the pullback of Ks plus B minus S restricted to S plus E restricted to S prime. So I'm confused about the E minus S prime. The E minus S prime doesn't make any sense. There's a mistake. It's just E. I was saying I was having a hard time recovering E minus S prime because it's only E restricted to S prime, right? So if I do the computation for B minus S, I end up with E restricted to S prime, which is what I have there, minus the pullback of D restricted to S prime. So this is essentially, by definition, and a teeny bit of work, I of B minus S restricted to S, comma, D restricted to S. Okay, now there's only one last thing that remains to do is to show that R1 F lower star of E minus round down F upper star of D minus S prime is equal to 0. This is what we need. And there's only one way that we can win is by applying Kawamata-Vivek vanishing. So let's think about what that gadget looks like. So E minus the round down of the pullback of D minus S is Q linear equivalent over X to Kx prime plus B prime plus the fractional part of D. Okay, so let's look at that. It should be, so over X, Kx plus B is 0. E corresponds to Kx prime plus B prime. And I think I have a typo here. This looks like this guy here should be minus S prime there. I think that's what I'm getting, right? Right, because E minus S prime from the first equation will be Kx prime plus B prime minus S prime. And then the pullback of D, so the only thing you need to observe is that round down of the pullback of D plus fractional part of the pullback of D is the same thing as the pullback of D, which is Q linear equivalent over X to 0. Okay? Okay, so if this wasn't here, this would just be the usual Kawamata-Vivek vanishing, right? Because this is a Cartier divisor, which is linear equivalent to a KLT pair plus 0, which is Fnef and F big. Okay, so now the question is, well, you actually have, it's not quite KLT because you have some stuff of coefficient 1. But now the point is, so you have to sort of, it's a mild generalization of Kawamata-Vivek vanishing. The point is that every strata of this divisor is mapping birationally onto its image. So I forget what that generalization of Kawamata-Vivek vanishing is called, but it's easily seen to apply to this situation too. You can easily prove it by induction on the number of components of this and dimension. So that's an easy exercise to prove, and I won't get into it. Okay, so we have these short exact sequences. How do these relate to lifting sections? Yes?
So when you wrote what you meant was after taking L.4 stuff.
Well, okay. I wrote in my clumsiness, I just wrote F low star here, and I meant through the process of pushing forward, you get, so yes, it's not equality, obviously. And then the next line is the R1 F low star. So the next one is a proposition with the same notation as above. Let me not write it in the relative version. I'll write it in the absolute version. Suppose that N is Cartier. And N minus D is ample. Then H, all higher homologies, in fact, of I, B, D, Kx plus B plus n is equal to 0 for every I greater than 0. And so we get a surjection from H0, I, B, D, K, X plus B plus N. Okay, so let's stare at this for a minute. So I take the above short exact sequence of ideals, and I'm twisting it by a Cartier divisor, kx plus b plus n. Remember, xb is log smooth, right? Cartier divisor. So it stays exact. I'm claiming that h1. Okay, so they have a very similar nature. So I'm claiming that h1 of this guy, in fact, the way I've written it is h1 of this is 0, but by the same argument you can see that h1 of this is 0. And so you get surjectivity between h0 of this guy and h0 of that guy. So what that tells you is it's not giving you a way to extend all sections from a divisor to the ambient variety, but you can extend those sections that vanish along this ideal. So you can extend sections of kx plus b plus n restricted to S, which vanish along the ideal b minus s restricted to s, b restricted to s. So it doesn't allow you to extend all sections. It allows you to extend some sections. Of course, you know, if D has very mild singularities, then this ideal is 0, so you can extend all sections. But life is not always that easy. So this is some version of Nado vanishing. And this ideal is sort of measuring where this pair is not DLT. So you can extend sections that vanish along the non-DLT locus of this pair, roughly speaking. Okay, so I should attempt to prove this. Go ahead.
Awfully confused. The sections of KS plus B minus S plus N restricted to S. You are subtracting B minus S. Where did the minus S go?
Where did what minus S go? Oh, you're wondering about this vanishing versus I really need...
No. When you write the projection, that one is KS. KS is... You're right. I forgot the adjunction. I apologize.
No problem.
Yes, I apologize. Yes. KS is KX plus S. Sorry about that.
No problem.
Sorry, I was stupid.
Yeah, so in order to get this extension, I may need that n minus d minus s is ample, actually, right? Right, because I'm supposed to apply it to this ideal here. So I would want the vanishing of that.
Sure. Sorry. So we tried to prove this restriction algebra. If you take the section from the restriction algebra, you can...
Right.
Like when you are taking some K section from KS plus theta,
Yes.
and that would extend the whole thing.
Yes.
What's the relation between that with N and D?
With n and d.
You will tell us.
Yes, hopefully we'll get to that. But somehow, I think the only thing you can take off from this at this point is that somehow you have to account the sections will have to vanish along some locus. And that locus, at the end of the day, is going to be the stable base locus of the linear series. That's where that is coming from. Okay, so let me see if I can quickly give a proof of this. So as before, f from x prime to x is a log resolution, which is an isomorphism at generic point of each strata of B. And just as before, I'm going to write that kx prime plus b prime is the pullback of kx plus b plus e, and that s prime is the strict transform of S. And now I'm going to pick F. So assume that this, well, I don't have to assume actually. So I can pick F, a Q divisor, effective Q divisor, such that minus F is F ample. And probably for good luck, I want to say that F is F exceptional. And I want to assume that x prime, there's a typo in my notes, I bet that what I want to assume is b prime plus the fractional part of the pullback of D plus F is DLT. So I don't know if I've talked about DLT, but what DLT means, so that means that there exists an open subset U containing x prime such that when I restrict, so when I look U, b prime plus, well, in this case, I don't need to tell you what DLT is because this divisor here has simple normal crossings, right? So you should just think of it as log canonical and simple normal crossings. So that, morally speaking, is what DLT is. There's a slightly more general version. So, right, because we took a log resolution, F is an exceptional divisor, so everything inside has simple normal crossing. I just have to check that there's nothing with coefficient greater than 1. So B prime is just the strict transform of B, so neither this nor that. By assumption, D does not contain any component of B prime, so the coefficients along B prime are less or equal to 1. F, ignore F for the time being. This is a fractional divisor that intersects this divisor transversely and has coefficient less or equal to 1, so we're in good shape. These divisors here, well, they could have something in common with this guy, but I can assume that the coefficients of F are arbitrarily small, so I can guarantee that this is DLT. In fact, the only stuff with coefficient 1 is the strict transform of the divisor B. So, you know, it's a bit of a fancy name for a simple observation. Okay, so now let's see. I want to compare E minus the round down of the pullback of D plus the pullback of Kx plus B plus N. It should be equal to Kx prime plus B prime plus the fractional part of the pullback of D plus F plus the pullback of N minus D minus F. Okay, let's check this. It's a long equation, but it should be ridiculously simple. Okay, so Kx prime plus B prime is a pullback of Kx B plus E. So E, pullback of Kx plus B, Kx prime plus B prime. Those match up. then what do we have? We have the round down of the pullback and the fractional part. Together, those add up just to the pullback of D. There it is. So we've accounted for that. And now the only things left are a plus F and a minus F. They're going to cancel. And then there's a pullback of N and a pullback of N. Those things match up. Okay, so if they're exactly the same, why do I bother rewriting it? Well, because I'm supposed to now observe that something is Nefan big or ample, and I can apply Kawamata-Vivek vanishing. So this is my, ignore this part, this is my Cartier divisor, which is of the form, let's see, what in this picture is, I had assumed that something, n minus d is ample. This guy here is ample. Pullback of this, relatively ample. So this gadget here I can assume is ample. Okay, that is ample. And this is, well, okay. So this guy here is DLT. Right? Remember, it would be KLT if these coefficients were actually strictly less than 1, but they're actually equal to 1. Okay. When you have a situation where you have some coefficients equal to 1, but you have an ample divisor, you can actually take a teeny bit of those coefficients and put them in here. Being ample is an open condition, so it's preserved. And now you have a situation in which Kawamata-Vivek vanishing applies. Okay. So, right, so you can think of it, morally, it's KLT plus ample now. Okay, so that tells me that certainly it tells you that Rj F lower star of Ox E minus the round down of F upper star of D is equal to 0 for every I greater than 0. And it also tells me, right, so this is the gadget that gives you the multiply ideal. But then, if I look overall, then the cohomology of I, B, D, Kx plus B plus N will be equal to the cohomology of E minus the round down of the pullback of D plus the pullback of Kx plus B plus N, which is 0.
Sorry, Chris.
Yes?
Where did the plus F upper star Kx plus B plus N go?
I'm just looking at the push forward of this. So that guy is numerically trivial. This is just a relative, so you have,
Okay, sorry.
yeah, so I don't really need to say it because I already waved my hands before and said that higher direct images vanish, but I want to emphasize that since the higher directed images vanish, the cohomology of these groups are just the cohomologies of these groups.
Yes.
And now the cohomology of these groups are 0 by the usual Kawamata-Vivek vanishing. So this is Kawamata-Vivek vanishing.
Is this what people call Hacon-Macron extension theorem?
We're not quite there yet. This is a warm up. A warm up to this. Here. So
this is not.
This is not. But I am now ready to state the precursor to the extension theorem. So this is. Okay, let me state it, and I'll tell you why it's not quite the right thing yet. So in the base point free theorem and the non-vanishing theorem, we applied Kawamata-Vivek vanishing. Here we do the same thing, but we do it inductively. We apply it infinitely many times. And we do that twice. So that's why it becomes a little bit more complicated. But Okay, so let me write the statement. Theorem. So we have x, s plus b plus d is going to be...
This HM extension theorem is this theorem.
This is it in the not quite optimal version. Yeah.
And this is Hacon.
Yeah. This is somehow it's a highlight. It won't look like it look like a big mess, but then yeah, it does exactly what you want. Projective, log smooth, such that the round down of b is 0 now. S wedge b is also 0. Oh, gosh. S plus b wedge d is 0. So, I mean, I've written down 3 divisors. They shouldn't have anything in common. That's what I'm trying to say. Now, delta is another divisor, which is s plus b plus p, where p is nef, and kx plus delta is Q-linear equivalent, let's say, to this divisor d. And I pick a positive integer, so pick k, some positive integer, such that kp and kb are integral. And h, something sufficiently ample. Okay, now I can state it. Then, for every element in this restricted linear series, and u in H restricted to S, and any positive integer L, we have L sigma plus U lifts. Okay, so you look at this and your head hurts immediately. So let's try and put a little bit of order. Really, we want to extend sections from something like this. Pretend maybe P is 0, right? It helps to have a bit of flexibility in your statement. Pretend P is 0. You have here sections of some nice adjoint linear series on S that you want to extend to the ambient variety. Okay? So this is the section that you want to extend. Now, can you extend it? Well, I'm saying that maybe I can't extend this section, this divisor here on the nose, but if I pick any multiple of it and I add a fixed sufficiently ample divisor, then I can extend it. Right? So it's not somehow then what you want to say is, and that's the full extension theorem. What you
I'm confused.
yes.
We are talking about K plus S plus B. Where did P come from?
P is just to give you a bit more flexibility. Oh, there's no P here, you're saying. Wait, no, there is. Okay, so, you know, like when you prove these sort of, what they call Castelnuovo-Mumford regularity things, sometimes you add just, you know, for any Neff divisor, you also get base point free.
My question was, we were looking at the KS
Okay,
plus,
so think P equals 0, right? P equals 0 is the case you're interested. Yes. But maybe for some flexibility, I will need to be able to allow a Neff divisor eventually.
Or P could be 0.
Yeah, P could be 0, right? I'm not requiring anything of P. Well, I'm requiring that Kp is integral. So if P is 0.
Oh, I see.
I'm requiring almost nothing of P, so.
Oh, so P is
Right. Then I'm making this annoying assumption, right? So now we're sort of going backwards. We have this annoying assumption. Kx plus d is Q equivalent to d, right? And what am I requiring about d? I'm requiring that d intersects the other stuff, simple normal crossings. Well, you can always achieve that by blowing up. The important thing is that d does not have any component of s plus b. So what you should think of, you're looking at the non-terminal valuations of this. D does not contain any of those, right? So this is like saying the base locus of this linear series, kx plus s plus b, the linear series that I'm interested in, does not contain any strata of s plus b. That's the thing I already warned you about.
So in general, it means that is it a generalized non-canonical pair? A generalized non-canonical pair?
Well, yes, I guess. At the time, generalized log canonical pairs didn't really exist, but yes.
So you're saying a little bit with M-code divisor, so you mean that the junction, inversion of our junction flux?
For generalized log canonical pairs? Yeah, that's correct. Yeah. In fact, there's a student of mine who's writing a preprint on that. He's pretty much done. But okay, so yeah. So anyhow, so this, at first sight, the statement looks crazy. It really is doing exactly what we want, apart from this extra ample. So then the next thing you want to do is you want to say, okay, wait a second. So let's take L sigma plus U, and let's divide this down by L, right? And, sort of asymptotically, we're getting what we need, right? You're extending sigma plus a little error term. Kawamata-Vivek vanishing allows you to kill that error term.
How?
Well, that's the next little result that I need to prove. But but that's when Hsu proved his deformation invariant of Perugino, that's exactly how he proved it. First, he shows that if you have a morphism from x to t, he shows that H0 of mkxt plus ht is constant, meaning that for a fixed ample divisor, sufficiently ample divisor, any multiple of m, you can extend sections from a fiber to the whole space. And then he shows that this implies that H0 of mkxt is constant. And in the algebraic world, we still don't know how to do this, except when kx is big. In that case, we can use Kawamata-Vivek vanishing to do that step. In complex analysis world, he knows how to do it. He uses some very careful analysis to show that it works, even if the Kodaira dimension is not maximum. Okay, so I have run out of time. So what I will do next time is maybe I'll prove this statement in full generality. I might not be able to prove that I can sort of get rid of this extra term, but I'll certainly make the statement of the optimal version of this, and then I will show you how that implies the existence of flips. So that's the goal for next time. Okay, and I didn't go over time today.